Dr. Judith Curry is president and co-founder of the Climate Forecast Applications Network. CFAN translates cutting-edge weather and climate research into forecast products that support the mitigation of weather and climate risk on timescales from days to decades. CFAN supports the energy sector with extended range probabilistic forecast of temperature extremes, severe convective weather, hurricanes, fire weather, and renewable energy. Dr. Curry is Professor Emerita of the Georgia Institute of Technology, where she served as chair of Earth and Atmospheric Sciences for 13 years. Her expertise is in climate dynamics, extreme weather, and decision-making under deep uncertainty. She is a fellow of the American Meteorological Society, the American Association of the Advancement of Science, and the American Geophysical Union. If we are all ready, Dr. Curry.
Thank you, and good morning. The climate crisis can be summarized as it's warming. The warming is caused by us. Warming is dangerous. We need to urgently transition to renewable energy to stop the warming. And once we stop burning fossil fuels, sea level rise will stop and the weather won't be so extreme. Last August, the Intergovernmental Panel on Climate Change, or IPCC, issued its sixth assessment report. In response, the Secretary General of the UN stated that this is code red for humanity. In my talk today, I'm going to present you with a different perspective on the climate change problem and how we can approach solutions. So what's wrong with the crisis narrative? It's my assessment that we've vastly oversimplified both the problem and its solutions. The complexity and uncertainty surrounding climate change is being kept away from the public and policy debates. Rapid reductions in emissions are technologically and politically infeasible on a global scale. And finally, the climate crisis narrative gets in the way of real solutions to our problems. Even people that don't know much about climate science have heard that 97% of climate scientists agree. But exactly what do they agree on? Not nearly as much as portrayed by the media. Everyone agrees that surface temperatures have increased since 1880. Humans are adding carbon dioxide to the atmosphere, and carbon dioxide and other greenhouse gases have a warming effect on the planet. However, there's uncertainty and disagreement on the most consequential issues. How much of the warming has been caused by emissions, how much the planet will warm in the 21st century, whether warming is dangerous, and how we should respond to the warming to improve human well-being. For policymaking, the most consequential issue is how much warming we can expect in the 21st century. This figure from the latest IPCC report shows climate model projections of global surface temperature anomalies out to 2100. There's a large range of warming shown in this diagram, from 3 degrees to 8 degrees Fahrenheit above pre-industrial temperatures. We've already warmed by more than 2 degrees Fahrenheit. So whether the future warming is on the low end or high end has huge implications for climate policy. The largest amount of warming is associated with an extreme emissions scenario, SSP 8.5, shown by the purple curve. The large amount of uncertainty in 21st century projections of surface temperature is associated with the amount of emissions, the sensitivity of the climate to these emissions, and finally, there's substantial uncertainty about the relative importance of natural climate variability. On the previous slide, recall that the largest amount of warming was associated with the emissions scenario, SSP 8.5. The IPCC assessment report regarded the 8.5 scenario to be our most likely future, and it was referred to as the business as usual scenario. However, it's becoming increasingly apparent that the 8.5 scenarios are implausibly high, if not impossible. The gray lines show emissions projections made by the International Energy Agency out to 2050. The IEA projections show fairly steady emissions through 2050 that are much lower than the 8.5 scenarios. The IEA projections are even somewhat lower than the IPCC's medium emission scenario, SSP 4.5. Nevertheless, the most recent IPCC report emphasizes the 8.5 scenario. Not surprisingly, this extreme emission scenario is a source of alarming impacts. The second major source of uncertainty is the sensitivity of global temperatures to a doubling of carbon dioxide, shown on the right. For decades, the likely range of climate sensitivity has been between 1.5 and 4.5 degrees centigrade, which is reflected by the assessment from the IPCC AR6 published in 2013. The red bars in the figure show the range of climate sensitivity from the most recent climate model simulations, ranging from 1.8 to 5.7 degrees. These values are overall much higher than those from the AR5, whose highest value was 4.6 degrees. In spite of the larger range from the climate models, the most recent IPCC AR6 substantially narrowed the likely range of climate sensitivity to between 2.5 and 4 degrees, indicated by the vertical blue lines, rejecting the highest values from the climate models. However, this narrowing of the range is disputed, particularly on the low end. The whole issue of climate sensitivity to increasing carbon dioxide remains unsettled. But the bottom line here is some good news. The extreme tail risks from global warming associated with very high emissions and high climate sensitivity have shrunk and are now regarded as implausible. So what is our best estimate of the amount of warming expected in the 21st century? The closest emissions scenario to the projections from the International Energy Agency is the medium emissions scenario, SSP 4.5. The recent IPCC report provides constrained projections that includes only the climate models with values of climate sensitivity between 2.5 and 4 degrees centigrade. The IPCC's best estimate for warming by 2100 is 4.9 degrees Fahrenheit, relative to a pre-industrial baseline for the period 1850 to 1900. The relevant policy targets of 1.5 and 2 degrees centigrade, indicated by the dashed lines, reflect temperature range relative to this pre-industrial period. We've already warmed by 1.3 degrees centigrade or 2.3 degrees Fahrenheit. The IPCC's best estimate has us crossing the 1.5 degree threshold in about 2030 and the 2 degree threshold in about 2055. There are numerous reasons to expect that the overall warming will be lower than the IPCC's best estimate. The current emissions trajectory is running below the 4.5 scenario. Lower values of climate sensitivity would also delay crossing these thresholds. The other factor to consider is natural climate variability. Major volcanic eruptions would have a cooling effect. A solar minimum is expected in the 21st century following the grand solar maximum that occurred in the late 20th century. Natural variability associated with the large-scale ocean circulations is also expected to contribute to cooling in the coming decades. We need to recognize that how the climate of the 21st century will play out is a topic of deep uncertainty. Once natural climate variability is accounted for, it may turn out to be relatively benign, or we may be faced with unanticipated surprises. The next area of disagreement takes us away from science and into the realm of values. How dangerous is global warming? The IPCC fifth assessment report used a burning embers diagram to portray reasons for concern. The level of concern increases with the amount of global warming. Note that the IPCC does not use words dangerous, crisis, or catastrophe in its reports. Rather, it refers to reasons for concern. Any evaluation of dangerous climate change must confront the Goldilocks principle. Exactly which climate state is too hot versus too cold? Some answer this question by stating that the climate we're adapted to is just right. However, the IPCC refers to a pre-industrial baseline in the late 1700s. Why anyone thinks that this is an ideal climate is beyond me. This was during the Little Ice Age, the coldest period of the millennia. Think George Washington and the horrible winters at Valley Forge. While the categories of concern in the burning embers diagram seem a bit nebulous, the sixth assessment report focused on extreme weather and climate events. Let's take a look. The recent IPCC report identified an increase in the intensity and frequency of heat waves, but a decrease in cold waves. The decrease in cold events is actually very good news. Numerous studies have found that there are more deaths from cold events than heat events by as much as an order of magnitude. The recent IPCC report also identified an increase in the frequency and intensity of heavy rain events. The IPCC looked at the period since 1950 in assessing trends in extreme events. However, looking only at the record since 1950 can lead to weather amnesia. New Jersey is facing the prospect of increased flooding. New Jersey is rightfully concerned about impacts from hurricanes, but these impacts are not necessarily worsening as a result of global warming. The worst hurricane to strike New Jersey in the historical record occurred in 1821, a Category 4 hurricane with a 13-foot storm surge. Hurricane Ida recently caused 7 inches of rain in New Jersey over 2 days. How does this compare with the historical record? Central Park in New York City has a data record that goes back to the 1860s. The highest daily rainfall accumulation occurred during 1883, over 8 inches. Looking at the historical data of extreme events helps us avoid weather amnesia. Further, it reminds us that even worse extreme events have occurred in the historical record, and that elimination of fossil fuel emissions isn't going to prevent extreme weather events. The recent IPCC report concluded that it's likely that the global proportion of major hurricanes, which are Category 3 and higher, has increased over the last 4 decades. The actual data is shown on the right. You can see that the actual number of major hurricanes does not show a meaningful trend that can be distinguished from the natural variability. The left-hand diagram shows the number of major hurricanes that have made US landfall since 1900. The year 2005 stands out as the highest, but 2005 was followed by a period of 11 years with no major US hurricane landfalls. Also, there were a large number of major hurricane landfalls during the first half of the 20th century, when surface temperatures were significantly cooler. The large amount of natural variability makes it difficult to identify meaningful trends in hurricane activity, and even more difficult to attribute any trend to man-made global warming. Okay. Sea level rise is an unambiguous impact of global warming. This figure shows a sea level record for Atlantic City. Since 1910, sea level has been rising at a steady rate of 1.36 feet, or 16 inches per century. New Jersey's coastal sea level rise is somewhat larger than the global average, owing to local sinking from geologic processes and the extraction of groundwater. In 2019, a team of scientists led by Rutgers University prepared a report entitled New Jersey's Rising Seas and Changing Coastal Storms. By 2100, for the medium emission scenario, the Rutgers report predicted a likely range of sea level rise to be between 2 and 5.1 feet. New Jersey's plan for protecting against climate threats, or PACT, adopted 5.1 feet as the basis for its regulations. In January 2021, I was contacted by Ray Cantor to provide an independent evaluation of the projections in the Rutgers report. The main conclusion of my report was that the Rutgers projections are substantially higher than the IPCC projections, owing to their method of incorporating extreme scenarios of instability in the West Antarctic ice sheet. This figure is from the most recent IPCC report. The left column shows projections of global mean sea level to 2050, and the right column shows projections to 2100. The middle row, circle in red, shows projections for the medium emissions scenario. Looking at the 2100 projections, the yellow bar indicates the likely range from the latest IPCC report, with an upper value of 2.5 feet. Accounting for the local effects for New Jersey produces a value of 3.1 feet at the upper end of the IPCC range. This value of 3.1 feet is substantially lower than the 5.1 feet cited in the Rutgers report. The latest IPCC report reinforces my previous assessment that the sea level rise projections from the Rutgers report are far too high. In evaluating the dangers of climate change, it's important to assess how global societies have dealt with the warming that we've already seen. So far, the world has done a decent job at adapting to weather extremes and climate change. The upper left figure shows the change in yield for major crops, with yields for many crops doubling or even quadrupling since 1960. The figure in the lower left shows losses from global weather disasters as a function of GDP. The spikes are associated with years that showed large losses from Atlantic tropical cyclones. Overall, for the past 30 years, there has actually been a slight decline in losses. The diagram in the lower right shows the number of deaths per million people from weather and climate catastrophes. Over the past century, climate change related deaths have dropped by 97%. Under the auspices of the United Nations, the world is attempting to reach net zero in carbon emissions by 2050. This diagram from the International Energy Agency illustrates the challenge. The blue curve shows expected emissions based on policies that are currently in place. The yellow curve shows pledges that countries have made as part of the Paris Agreement. And the green curve shows the path we should be on to reach net zero by 2050. There's a large gap between our current and committed policies versus the net zero target. There are numerous impediments to reaching net zero: waiting for better technologies, costs of the transition, and politics surrounding natural gas and nuclear energy. But most importantly, there are concerns about maintaining energy security during the transition in terms of electricity reliability and cost. The path to net zero by 2050 is generally regarded to consist of the following elements. The fundamental premise is to eliminate fossil fuels, then replace fossil fuel generation with clean energy, focusing on solar, wind, and biofuels. Nuclear remains controversial, although there's a recent surge of support in Europe and Japan. There's also an implication of austerity in terms of using less energy. And in doing the carbon accounting, it's very difficult to achieve net zero by 2050 without carbon capture and storage. However, we do not currently have the capability to accomplish this at anything close to the needed scale. The International Energy Agency finds that there is a possible but very narrow pathway to net zero by 2050, provided that there's a huge leap in energy innovation and major efforts to build new infrastructure. Other analysts find that reaching net zero globally by 2050 is a social and technological impossibility. Some countries and states can reach net zero by 2050 relatively easily if they have a large amount of hydropower or an existing base of nuclear power. However, it will be very difficult for most other regions, particularly in the face of growing population and desired economic growth. But even if we can't meet the targets, we should try anyways, right? Well, the fundamental problem is the level of urgency. I've shown that the perception of a crisis and the level of alarm is overblown. Targets that are too stringent lead to decisions that aren't beneficial in the longer term. Another key issue is that the demand for electricity is growing. We need much more electricity, not less. Going on an energy diet like we did in the 1970s is off the table. We don't just want to survive, we want to thrive. We need more electricity to support innovation and thrivability in the 21st century. A more pragmatic approach to dealing with climate change drops the timelines and emissions targets in favor of accelerating energy innovation. Once the stringent targets are removed, you have space to imagine what the infrastructure for our 21st century electricity system could look like. With new technologies for electricity generation, a 21st century transmission infrastructure, and an entire system that's more resilient to extreme weather events. Compare this vision against the current plan for urgently implementing 20th century wind and solar technologies, patching them into the existing transmission grid, eliminating backup power sources of natural gas and nuclear, and then hoping for the best. This is where urgently working towards net zero by overinvesting in wind and solar is leading us. Nations and states are coming to grips with their overdependence on wind and solar, notably California, the UK, and Europe. In 2021 so far, offshore winds in the North Sea have provided 7% of the UK electricity, compared to 25% in 2020. Concerns about not meeting electricity needs next winter are resulting in near-term reliance on coal in Europe and Asia. You can avoid this situation by hanging on to your existing nuclear and natural gas generating capacity. Nuclear and natural gas are key enablers for reducing carbon emissions in the near term. Natural gas is essential for keeping energy prices in check while we invest in the technology and infrastructure necessary to attain net zero in the future. We can be sure that the future of the 2030s will look very different from the future of today. In evaluating clean energy technologies, extend your horizon to the 2030s and build in the capability to adopt new technologies in your planning process. Consideration of these factors can lead to a better and even cleaner electricity system by mid-century, including new technologies such as small modular nuclear reactors and advanced geothermal. Thank you, and I look forward to your questions.
Thank you, Dr. Curry. Before I turn it over to the audience, I have a question for you. You've laid out a scenario for the future where the more extreme climate scenarios being pushed by advocates and amplified by the press may not necessarily be what we should really be expecting in the 21st century. And you proposed a more pragmatic and thoughtful way of approaching our energy solutions to get to a net zero. Yet, as you know, we are being bombarded by press statements on a daily basis, basically using 8.5 as the scenario that's going to happen. So how do we as a business community communicate in a world where we're being told that we have 12 years to save the planet?
Well, I think the best way forward is to really just change the conversation. And here's where business leaders can charge. If you focus on a 21st century vision for electric power infrastructure with abundant, cheap, and electricity, I mean, everybody will be on side. Sell prosperity and thrivability as the motivations for this. Support innovation, not greenwashing, which the energy industry is often accused of, but come up with a real plan. It's time to listen to business and the engineers, not the politicians and the activists. If you come up with a good plan, even the climate activists will have a hard time objecting. But there's a big disconnect between the public dialogue and the crisis and everything versus the realities on the ground. We need, and business and industry leaders have an opportunity to bring this whole discussion back to reality.
Does anyone have any questions from the floor? Seeing none. And we are out of time, as well. So, Dr. Curry, I thank you for your attendance here today. Thank you very much.
Thank you.